Hello. In this video, we are going to discuss the polyhalogenation of alkynes. That will be the addition of either one or two molecules of halogen, which will be either 2 or 4 atoms of halogen to an alkyne. Recall that an alkyne has the general structure R1, then a carbon-carbon triple bond, and R2, where R1 and R2 can be either the same or different. They can be hydrogen or some alkyl group. For the halogen, the general structure will be X2, because all the halogens are diatomic. But the only two halogens that are important for addition to alkynes are chlorine and bromine. Fluorine reacts far too violently, and iodine reacts far too slowly to be important. Let us recall what happens when halogens react with an alkene when we have a carbon-carbon double bond. So let's use as our example the simplest of the alkenes, ethylene. And recall that when it reacts with a halogen, a key intermediate is the formation of a cyclic halogen ion. So it forms this trigonal structure, and then we have anti-addition of the anion to one of the two carbons. So recall, that is what happens when we have an alkene. Based on that, we would expect that if we have an alkyne, that the key intermediate would be the formation of a cyclic halogen ion. By direct analogy with what happens to an alkene. The curious factor is, depending upon which textbook you look at which source, some sources say that this type of structure is formed, and some say that it is not formed. So to test, we've run computed intermediate structures for the addition of halogen to the carbon-carbon triple bond. And curiously, in some cases, we do find that we have this formation of a cyclic structure. In other cases, we find that the positively charged halogen adds preferentially to one or the other of the carbons, often having an obtuse angle. So not only is it not an isosceles triangle, it is actually an obtuse triangle. Recall that the simplest and most important of the alkynes is acetylene, sometimes known as ethyne. So let's look at the mechanism for the chlorination. We recall that we have heterolytic cleavage of the chlorine-chlorine bond, so that the rightmost chlorine ends up with the electron, so it is negatively charged, and the leftmost chlorine is positively charged. Therefore, it is an electrophile. The carbon-carbon triple bond is electron-rich, so electrons flow from there to the positively charged carbon. So we end up with is a intermediate. The triple bond is reduced to a double bond. And in the case of acetylene, the calculations, in the absence of solvent at least, show that we do have formation of a cyclic chloronium ion as a intermediate. Then we have anti-addition. In this case, both of the carbon atoms are identical, so we are left with, as our product, trans 1,2-dichloroethylene. Please see the following figures, which show the computed reactants, products, and intermediates for the chlorination and the bromination of acetylene. Also see the first appearance of a table showing that compared to alkenes, it is slightly more difficult to halogenate an alkyne than an alkene. Part of the difficulty involves the difficulty in making this three-membered ring intermediate where one of the sides has a double bond. In other cases, when we don't have a cyclic intermediate, effectively what we have is a vinylic cation, which we know is not particularly stable. Now suppose that we have a sufficient excess of chlorine that we can continue to react the trans 1,2-dichloroethylene with more chlorine. We should already suspect what's going to happen from what we know about the halogenation of alkenes, that we have a heterolytic bond cleavage. The carbon-carbon double bond is electron rich. So we have flow of electrons from there to the positively charged chlorine, and we end up with the double bond being reduced down to a single bond. So while this looks somewhat cluttered, it's exactly what we imagined in the case where if we didn't have the previous chlorination, we have the formation of the cyclic chloronium ion, and then the final step is going to be the anti-addition of chloride by a backside attack here. This bond. So what we end up getting is two chlorine atoms on each of the carbons. So this is 1122 tetrachloroethane. Please now see the following computed structures for the reactions of the trans 1,2-dichloro and the trans 1,2-dibromo ethylene with chlorine or bromine and the resulting products, also showing the cyclic intermediate. Now let's look at the bromination of propyne, the 3-carbon alkyne. We have heterolytic bond cleavage of the bromine-bromine bond. We have flow of electrons from the electron-rich triple bond to the electron-deficient bromine plus, the bromonium ion. And we'd expect that we're going to get the formation of a cyclic bromonium ion structure by analogy with alkenes. The calculations show something else though. What they show is that we get reduction of the carbon-carbon triple bond to a double bond, which is what we'd expect. But then, rather than being bound to each of the 2 carbon atoms, it actually binds to the first carbon. And we know that when we add electrophile to one of the carbons, that the positive charge goes to the other carbon. So, while this might be somewhat unexpected, it makes sense in the fact that by bromine adding to the first carbon, we end up with a positive charge on the central carbon, therefore making a secondary carbocation. If bromine had added to the central carbon, the positive charge would have been on this carbon, and we would have had a primary carbocation. And we recall that secondary carbocations are far more stable than primary carbocations. So here we see application of Markovnikov's rule. So we have Markovnikov addition of the bromine plus to propyne. Then in the secondary step, we have anti-addition of bromide at the positively charged carbon. So as a result, our product has this structure. So we have the trans 1,2-dibromopropene. And this works exactly the same if we had reacted with chlorine. So please see the following computed structures for the reactions of chlorine and bromine with propyne, showing the intermediates, reactants, and products. Now, in the presence of excess bromine, we can further brominate this dihaloalkene exactly as we expect, in the sense of we have the heterolytic bond cleavage, we have flow of electrons from the double bond to the bromonium ion, but now we saw in the further reaction of acetylene and then the trans 1,2 dihaloethylenes that the intermediate ended up having a cyclic structure. Again, in this case, we don't get a cyclic structure. What we end up getting is in here, we get Markovnikov addition to the double bond. So we get addition to the first carbon again. Since we add the electrophile to the first carbon, that means the positive charge ends up on the second carbon. We recognize again that we are forming a secondary carbocation. If the bromine had added to the other carbon, the positive charge would have been on the first, and we would have had a primary carbocation, and we know that the driving principle behind Markovnikov's rule is that the more stable the carbocation, the more quickly it forms. So, the final step, as we'd expect here, is going to be anti-addition of the bromide to the carbocation. And we get so we notice that we have a 3-carbon chain, so this is a propane. So we have 1,1,2,2 tetrabromopropane. Please see the following structures for the bromination of the trans 1,2 dihalopropenes with either bromine or chlorine, seeing the reactants, the intermediates, and the resulting products. The next reaction we're going to look at is the reaction of 1-butyne with halogens. We're not going to write it all out in complete detail on the whiteboard because it follows very similar to our result for propyne. Once we add the first step, add the either chloronium or the bromonium ion, we end up not getting the cyclic structure, but we end up getting attachment of the positively charged halogen to the first carbon rather than to the second carbon, in accordance with what we'd expect from Markovnikov's rule. Please see the following structures for the bromination or chlorination of 1-butyne. After the electrophilic addition of halogen to 1-butyne, we end up getting a trans 1,2-dihalo-1-butene. And then when we add further halogen, as we are noticing as our pattern goes, we don't get the cyclic intermediate, but again we get addition of the positively charged halogen to the first carbon in accordance with Markovnikov's rule. Please see the following structures for the reaction of this type of compound with either chlorine or bromine. For our final example of an alkyne, we're going to look at 2-butyne, sometimes called dimethylacetylene. This compound is particularly interesting from the point of view of calculations in that when we add chlorine, we do not get a cyclic intermediate, at least according to the calculations, but when we add bromine, we do. So one thing which we notice as a general pattern is that we suspect if we have mirror symmetry, so that the left side of the triple bond is the same as what's to the right side of the triple bond, we are likely to get cyclic intermediates. Whereas we've noticed in every case where it was not symmetric, we never got a cyclic intermediate. Please see the following computed structures for the electrophilic addition of chlorine and then bromine to 2-butyne. Electrophilic addition of halogen to 2-butyne leads to a trans 2,3-dihalo-2-butene. So now we're going to look at computed structures for the reaction of this type of dihaloalkene with a further mole of either chlorine or bromine. Please examine carefully the following tables which show the computed enthalpies of activation and reaction for either the dihalogenation or tetrahalogenation of various alkynes. I definitely want to thank my viewers throughout the world for their kind attention. Have a good one.